All right, good morning, everybody. So we're into lecture deck 24, if you're following along in the lecture slides. So this is inheritance part 2. So remember at the end of last day, we ended up implementing two different kinds of counters, I suppose. So we had a counter that stops. We had a counter that throws an exception when you hit integer max value, right? So remember, we have a throwing counter. Right? We're going to extend, we turned our regular counter class into a superclass. Right? So we made some of its field, protected so that the subclasses could access the fields directly. Right? And so then we extended the counter class. Right? So a throwing counter does not have its own integer field to hold the count. Right? That int field belongs to the superclass and counter. Constructor. Remember, in your constructor, you should always call the superclass constructor on the first line. You should always call the constructor on the first line. At some point during the initialization process, you have to call a constructor. You have to call the superclass constructor. So the easiest way to deal with this is to always call the superclass constructor on the first line. The advanced method here throws an exception if the value happens to be equal to integer max value. Right? If it's not integer max value, it just goes ahead and adds 1 to it. All right, so you don't have to do this with inheritance. Right? So notice that our counters, the only thing that differs in them is that something happens when it hits the maximum value. Right? So we used inheritance to create separate classes. The separate classes essentially overrode advance, and that's all they really did. Right? So there is an alternative approach to this. Right? So instead of using inheritance, what you can do is that you can, right, so remember, they all differ in this one method. So what you can do is you can create an object that can deal with this one method. Right? And so what you do is you make an interface, call it something like advanced interface or something like that, right? That interface has one method in it called advance, right? And now you can make, or somebody else can make, as many different types of classes that implement the advanced interface. And now your counter just has an object of the interface type. Right? And then here you just call the object's advanced method and let it deal with it. So you can get rid of inheritance altogether by using an interface instead. Right? I'm not going to actually show you how to do that here. I guess you kind of saw, I guess the player interface from assignment 5 sort of did that. All right, so what about equals? So we're in the interesting case here where you've got 3 different kinds of counters. And it might make sense to compare the different kinds of counters for equality. Right? Because all you care about in the counter is whether or not the value is equal. The problem with our current counter class is that the current counter class uses getClass in its equals method. Right? So let's go look at that. Right? So this is our current implementation of equals in counter. Right? We do the usual 3 things. Right? So check if this is equal to obj. Right? So is this object the same as that object? If so, return true. Right? We check if obj is null. So if it's null, equals should always return false. Right? And then we compare the classes of the 2 objects. Right? So if the counter, so this is always counter. So if the counter class is not the same as the class of that object, right, we're going to return false. So this only lets you compare types that are exactly the same type. Right? And so in other words, this lets you compare a counter to another counter for equality. But it won't let you compare a counter to, say, a stopping counter or a throwing counter for equality. Right? Because the type of obj will be throwing counter or stopping counter. Right? The type of this is counter. Those aren't the same, so this will always return false. So this doesn't work if you would like to compare different types of counters for equality. Right? So for example, I have a counter C1 and C2. Right? Their values are both 0. They're both big C counter objects. Right? So C1 equals C2 should return true. Right? If I have 2 stopping counter objects, now remember this is in counter. Right? We haven't overridden equals in stopping counter. So stopping counter gets this equals method. Right? So now in this equals method for stopping counter, it's stopping counter for this and whatever class for obj. right? So if C3 and C4 are both stopping counters, right, then we can compare them for equality. So this will be true as well, right, because their values are both 0 and they're both of the same type. So that's all fine. But if I make a counter and a stopping counter object and try to compare them for equality, right, this line here immediately causes false to be returned, right? And in this particular example, it kind of makes sense that you want to compare different kinds of counters for equality, because all you want to do is compare their value. Right? Similarly, if we try to compare a stopping counter to a throwing counter, or the other way around, right, throwing counter to stopping counter, that's going to return false, again, because that line right there, right, that condition there is true, right? The class of the object being used to call equals is not the same as the class being passed into the equals method as obj, right? So that will always return false. All right, so sometimes, but not all the time, right? So sometimes when you're implementing a hierarchy of classes, you would like to compare the subclasses for equality, right? And so you have to change your implementation of equals and instead use instance of, right, which we haven't seen yet. If you read the lecture slides or the course notes, you'll have seen instance of already. Okay, so what you do in equals is you start out the exact same way, right? You check, is this object equal to obj, right? Are they same objects? If so, return true. All right, you can now remove the test for null and the test for get class. And instead, you replace it with an instance of test. Do I tell you what it does here? No, I don't tell you what it does. Okay, you replace it with an instance of test. All right, so what instance of does, right? So reference here, some type or some other object here, right? So here we have obj. Oh, wait, this is wrong. Oh, no, this is right. Sorry. Obj, instance of counter. So what this is asking is obj, right? Is it a counter object or is it a subclass of counter, right? So that's what instance of does, right? It returns true if obj is from a class that has counter as one of its ancestors, right? So this will let you test obj if obj is obj. So if not obj instance of counter, right? So if obj is not a counter object, or if it's not a subclass of counter, right? Now we return false. If obj is a counter object, or if it's a subclass of counter, right? Now we get down to here, right? So once we get to here, right, we know that obj is some kind of counter, so I can cast obj to a counter object here, right? Store it in a field called other, in a variable called other, right? And now I can access its value, right? And compare the value of this counter and the other counter, right? And so you would replace equals in the counter class with an instance of based equals method, and that lets you test subclasses for equality. One thing not to do is that you don't override equals again in the subclasses, right? So in stopping counter and in throwing counter, you don't replace equals, right? You rely on the equals method that's defined in the superclass. It turns out that if you override equals in the subclasses, you will run into problems that are beyond the scope of this course, right? So you want to stop at the superclass, at the common superclass. You want to stop implementing equals at that point, right? Okay, once you make this change here, right, now you can make comparisons between counters of the same type, right? So counter equals counter, that's true, right? Stopping counter and stopping counter, that's also true, right? Counter and stopping counter, now I can compare them for equality. If their values are the same, that will be true, right? Stopping counter and throwing counter, or the other way around, right? Throwing counter and stopping counter, now comparing them for equality is true, right? Because our instance of test, obj is an instance of counter as long as obj is a subclass of counter, right? And so that lets you compare subtypes for equality in an inheritance hierarchy. Right. All right, was that, did anyone have questions about what I just talked about there as far as equals is concerned? Right, so you always have two choices when you implement equals. If you're not in an inheritance hierarchy, use get class. If you are implementing a superclass for an inheritance hierarchy, you have to consider whether or not you want to use instance of. Yeah. So number one, there's no purpose. Number two, if someone if someone if someone extends your class where you're using getClass, then they are prevented from using, they're prevented from comparing objects for equality if they don't have the exact same type. So it'll never work for them anyway. Right? Okay. Oh wait, sorry, you asked me why should you not always use instance of? Right, sorry, no, sorry, I was thinking, I had it the other way around, sorry. So why should you not always use instance of? So the reason you shouldn't always use instance of is because when someone overrides a subclass, there's a good chance that they're going to add fields to the subclass. I guess I have to sketch this out now. Now that you've asked the question, I have to explain it. Sorry, if you're watching this as a recording, you don't need to know this for the exam. And you won't be able to see what I'm writing on the blackboard anyway. Okay, so we've got a class. So I'm going to call them super and sub. Oops, sorry. Super. It has one field in it, right? Int x. Okay. And now you've got a class sub. So it's going to be the subclass to super. Oops, sorry. Extends super. All right, so it's often the case that when someone implements a subclass, I guess I should make that protected, they're going to add fields to the subclass, right? So for example, they'll add their own field, double. It doesn't matter what the type is here, right? They're going to add their own field called y, right? So in the superclass, if you use an instance of, okay, so this uses, it's an instance of equals, right? So in the subclass, you say, well, I've got this field y, so if I want two sub y objects to be equal, I have to test their y value as well, right? Probably, right? So the superclass is going to test x, right? Compares x. Okay, so what is this going to do, right? So it wants to compare x as well because x is one of its fields, right? But it's probably also going to compare y, right? So probably. So I'm going to show you how to do this in a little while, right? So it's probably going to call the superclass version of equals because the superclass version of equals knows how to compare the x value, right? Now it's going to compare, then compares y. Makes sense, right? Okay. So, oh, I can't, it's not a blackboard on the other side. All right, so now imagine what happens here. Okay, so super S, new super. Super, no, sub. Well, it doesn't matter. Super S2, new sub. Right, so we've got a superclass object and a subclass object, and I'd like to compare them for equality, right? S equals S2. Right, so that works. Right, everything's fine. S is a superclass object. So when you write S equals S2, you get the superclass version of equals. Right? That compares the x value of S and S2. Make sense? So compares x values only. Right? Now what happens if I flip it around? S2 equals S, right? Now what happens, right? So S2 is going to try to call, is going to get this version of equals, right? So it'll test the X value, right? Does it actually test the X value? Maybe, maybe not, right? So what happens here? So in here, you're going to call the superclass version of equals, right? There you're going to do, now you do instance of sub, right? So call the superclass version of equals, that tests the X value, right? Now if you get to here, so if the X values are equal, right, you now want to compare the Y value. But the only way you can access the Y value is if that thing there is a subclass object, right? If it's a superclass object, it doesn't have a Y value, right? Okay, so you're going to do an instance of subtest. That causes that to immediately return false. It's possible that this returns true because it only cares about the X value. And that has an X value because it is one of these, right? So that can return true, that returns false, and the equals contract says that must not happen. S equals S2 must be the same as S2 equals S. So you run into all sorts of problems if you use an instance of based test here and you don't prevent subclassing. And the subclass adds a field and uses it in equals. Why should it equal? So that instance of test allows you to compare them, right? You can't stop it now.
You can't stop it, but if S2 adds extra fields,
Yeah.
I would argue that that's a different thing than S, which is a super, which only has one of the fields, where S2 has 3, 4 fields. So I don't think that S equals S2 should return true in any case.
So how do you prevent it? The superclass doesn't know anything about the subclasses. So there's no way to prevent it, right? As long as that's a subclass, it's got one of these. If you use an instance of test, right, that you're stuck, right? You're going to you do allow the comparison to a subclass object, right? If you're designing so the rule or the advice that's given is if you're designing a class and you are not designing it strictly for inheritance, use getClass, and that prevents that problem there. If you're implementing an inheritance hierarchy, you have to think about whether or not you want equality between the subclass objects and whether or not it's meaningful. Right. That's why I didn't want to explain what was going on in the slides. Right. This is a very advanced topic for an introductory object-oriented programming course. That's the answer. Okay. Some of this code might seem funny to you if you're looking at it, right? So here I've got a counter object, C1, and I store a counter object in it, no problem, right? I've got a counter variable, C2, and I'm storing a stopping counter object in it. So it turns out that's legal, right? It's legal because, right, you can use a subclass, so stopping counter, anywhere where you need a superclass object, right? So C2 is a superclass, has superclass type, right? So I am allowed to store a reference to a subclass object in C2. Right, that's perfectly fine. Now the question is why does this work? Right, and the answer is because in Java, objects have more than one type. Right? So with the exception of big O object, right? If you have an object of type big O object, every other object has more than one type. So an object's type includes its own class type, all of its ancestor class types, and all of its interface types. Right, so here's our class point2. Right, now remember point2 extends object even though we didn't say it did, right? But it does in fact extend object. I think we got to the point where we implemented comparable, right? And so what types does point2 have? Well, point2 has its own type, so it's point2. It's also an big O object, so one of its types is big O object, and one of its types is comparable point2. Right? So point2 has 3 types. Our stopping counter class extends counter. Remember, counter extends object, right? So don't forget object when you count its types. And it implements comparable counter. So the type of stopping counter is the class itself. its immediate superclass, which is counter, any superclass that counter has, which is object, right? And it's any interface types, right? So it also has the type comparable counter. So every stopping counter object has 4 types. Here's string. If you actually look at the documentation for string, you'll see that string is declared as being final. So if you ever see a final class, that means this class cannot be extended, right? So it's impossible to make a subclass of string, which prevents that problem over there as well, right? You can't override equals, so you can't override the equals version of string because you can't subclass it. Right? String extends object and it implements 1, 2, 3 interfaces, right? So that every string object has the class type string, right? It has the superclass type object and it has all of the interface types as well. Right? So it's entirely possible for a class to have a dozen types. That would not be unusual in Java. Right? And so as soon as something has more than one type, you get into this, in object-oriented programming, once something has more than one type, you get into this notion called polymorphism. So if you look up this word in the dictionary, right, you'll see that it's the condition of occurring in several different forms. Right? Java has what's called subtype polymorphism. Right? Subtypes are substitutable for their ancestor types. Right? So string is substitutable for object, stopping counter is substitutable for counter, and so on and so on and so forth. Right? There's several different forms in object-oriented programming means an object has more than one type, right? Which we just saw on the previous slide. Right? This works because the type of an object includes the type of all of its ancestor classes. Right? So when creating a variable, right, you have a type here for the variable c, right? So we have counter c. So in this variable declaration, this says that c is C is a variable of type counter. Right? We say that the declared type of c is counter. Right? So when you use c, you can store, you can store a counter object or a reference to a counter object in c. Right? So c equals new counter. I can store a reference to an object having a type that is a descendant of counter. So c equals new stopping counter. Right? Or I can store null, indicating that there's no object referred to by c. Right? So c equals null. Right? This works. Oh, sorry. Right? Hey, where to go? Again, this works, right? Because your subtype objects, one of their type is counter. Right? So throwing counter, one of its types is counter. So I'm allowed to store that in a counter variable c. The opposite's not true. Right? So if I have throwing counter c, I cannot store a counter reference in that. Right? Because counter is the superclass. Right? The superclass is not substitutable for the subclass. Right? So throwing counter c equals new counter doesn't work. Right? A superclass variable can store a reference to a subclass type. Right? The opposite is not true. So the declared type in Java, it turns out to be important because it determines what methods you can use with that variable. Right? So here I've got obj, its declared type is big O object. Right? Now I can store any reference in this variable, right? Because object is the parent class of everything, is the ancestor class of everything in Java. Right? So I can, for example, store an array list reference in obj. Right? Now, what can I use obj for? Right? Well, big O object has a toString method, so I can definitely call toString. Right? Array list has an add method, but I can't call add using obj. Right? Because as far as the compiler is concerned, obj is a big O object. Right? And so you're restricted to what you can do with obj, to the methods that are defined by object or one of the subclasses of object of which there are none. Right? So the only thing I can do with obj is call a big O object method. The declared type determines what methods you can call using the variable. Right? So even though obj is an array list, I can't add anything to that list. Right? Not using obj. So here's a set, right? I'm going to store a tree set reference in T. I can call add because tree set has an add, because set has an add method, right? Remember, set is an interface in this case, right? It's not a class, right? But it does define a method called, it declares a method called add, so we can call add. Tree set is a sorted set. It has a method called first, right? So you would think that you could call t.first using your variable t here, but you can't, right? As far as the compiler is concerned, t is a big S set. Set does not have a first method, so you can't call first using t. Yes?
In the previous example, when you call obj.toString,
Yep.
does that use the object version of toString?
That's a good question. Which version of toString gets called here, right? So the way it works in Java is, I'm about to tell you how it works. So it's the runtime type of obj determines which version of the method gets called. And I'm about to tell you what the runtime type means in just a second. So to answer your question, it's the array list version of toString that gets called. What else do we got here? Oh yes, right. So again, it's basically the same point, right? It's the declared type of the variable that determines what you can do with it, right? So if I change t to sorted set, right? Sorted set is the interface for tree set, right? So it's a sub-interface of set that adds all of the sorted set methods, right? So if I change t to sorted set, I can call add. That method came from set, which is also in sorted set. I can now call first because first is defined or declared in sorted set, right? So now that works, right? And that works because the declared type has a method called first. Okay, now when you write C equals something, the something on the right-hand side, that determines the runtime type or the actual type of the object that is referred to by the variable. Right? So declared type is counter. Runtime or actual type is stopping counter. Right? So thing on the left-hand side, declared type. Thing on the right-hand side of the equal sign or the assignment operator, runtime type or actual type. Right? So the runtime type is stopping counter. Now the runtime type is also important in Java. It determines which version of a non-static method gets called when you use the variable. Right? OBJ, declared type is object. Right? Runtime type is counter. When I write obj.toString, I get the counter version of toString. Right? I can call toString because obj has a toString method. Right? It's of type object. So I'm legally allowed to call toString. The version of toString that you get is determined by the runtime type. Right? And that's why things like this print method here always works. Right? So if I declare a method called print, it takes in a big O object, I can always call obj.toString and pass that to println. That will print the string representation of any object in Java. Right? Why does this work? Because it's the runtime type of obj that determines which version of toString gets called. Right? The declared type object determines whether or not I'm allowed to call toString. Right? Big O object has toString, so that line of code is legal. Right? You don't actually have to do this. Println does this automatically for you. So if you call println within an object, it automatically calls toString on the object reference for you. So if I call print with a string, I get the string version of toString. Right? If I call print with a list, or an array list in this case, I get the array list version of toString. Right? If I pass in a date, so notice here, right? So here the declared type is string, the declared type is array list. Here the declared type is object. Right? I don't get the object version of toString here. Right? I get the runtime version of the object. Right? So I get the date version of toString here. Right? Runtime type, thing on the right-hand side, determines which version of the method you get. Okay, now if you really sat down and thought about this for a little while, this all looks a little bit strange, right? So if we go back here to this method right here, right? So you can write this class and compile it, and the compiler is perfectly happy with it, right? it'll compile this method no problem. If you put in a main method and it calls the method, no problem. Right? Notice that here, there's absolutely no way for the compiler to determine which version of toString should be called. Right? There's no way for the compiler. It doesn't know what the runtime type of OBJ is here. Right? Someone can write a program that passes in a string. Somebody else can write a program that passes in a date. Someone else can write a program that passes in one of their own objects. Right? The compiler has no idea which version, what type is getting passed in here. Right? So the compiler can't determine which version of toString to call. Right? The actual version of toString that gets called, that can't be determined until you actually run the program. Right? So using the runtime type to determine which version of a method that get to call is called dynamic dispatch or late binding. Right? Dynamic to indicate that it happens at runtime. Right? Dispatch is a word that means which version of the method should I call. Right? Binding, a different word that means which version of the method should be called. Late means after compilation, so at runtime. Right? If it was early binding, that happens at compile time. Right? Dynamic dispatch, which version of the method should be called at runtime. So after you've compiled your program and now you run it, which version of toString gets called. Right? So all that logic happens when you run the program. Right? So that example I showed you right there is it's a very simple example, right? But it illustrates the power of the fact that objects can have more than one type. Right? So it illustrates the power of polymorphism. Right? What can you do with polymorphism? Right? So when I write this method, right, I can look at the documentation of the class object. Right? That's all I have to do. All I have to do is look at the class object, and I see what methods are there. Right? I look at the toString method, and I see what does toString do for the class object. Right? Well, it returns the string representation of an object. Great. I can write code using the documentation or the contracts, preconditions, postconditions, class invariants, however you want to think about it, right? I just look at whatever object can do, right? And I can write code that will work or is supposed to work, right? Regardless of what type of object gets passed into this method, right? And so that's a very powerful thing to do, right? I can look at a superclass. I can look at what methods a superclass can perform, and I can write all sorts of code based strictly on the superclass methods, right? Anybody else can override the superclass methods if they do it properly. The code that I wrote, having no knowledge whatsoever of the subclasses, still runs correctly, right? So if you look at this class called collections in java.util, oops, sorry. Do I have a link to this? Let's see if this will open for me. Right. So you go and look at the documentation for the class collections. Make it a little bigger so you can read it. Wait, is this the right? Sorry, I may have the wrong link. Collections with an S. Okay, so I have the wrong link. I have collection, no S. Collections, there we go. Okay, so we go and look at the utility class collections. Remember, this is the class that operates on lists and sets in Java. Right? Here's binary search. Right? So there's a binary search. Right? It'll take in any list as long as the list elements implement comparable. That's what that question mark extends comparable means. Right? And it will search that list for that key. Right? It doesn't matter what kind of list it is, right? It could be a linked list, it could be a array list. You can make up your own list type. It'll work as long as you implement the list correctly, right? And it will perform binary search on that list. Where's add all? Add all, right? Add all takes in a collection, any set, any list. It doesn't matter what kind of set, it doesn't matter what kind of list. And it will try to add all of those elements to that set or list, right? It doesn't know what the type of list is. It doesn't know what the type of set is, right? You could create your own class that implements the collection interface that's not a set or list, and it'll still work, right? So by looking only at the contracts of collection, the methods that collection has, right, you can write methods like add all that will work with any kind of collection. Okay, inheritance 3. So it's deck 20, is it here? It is not here. Sorry. 24, where am I? Did I get to the end? I got to the end, okay. Sorry, I gotta download the next set of slides. So we're now on 25, inheritance part 3. We're going to cover as much as I can in the time that's left. I don't know how much that's going to be. Oh, I guess that's not important. I don't know why it's so small there. Okay. All right, so one thing you need to keep in mind is that in Java, when I say substitutability, right, or when you implement an inheritance hierarchy, right, what's really implied is this thing called Liskov substitutability. So this is named after Barbara Liskov, Dr. Barbara Liskov, who first described this principle. Click on that link if you want to find out about her. She's one of the Turing Award winners, so essentially the Nobel Prize in Computing Science. There is a formal mathematical definition for this, which I don't think is important in this course. Right? So what you need to remember is, for substitutability, is that subclass objects must behave the same as objects of their supertype. Right? So remember when you are writing the Java doc for methods in a class, right? You describe the preconditions and the postconditions of the method. Right? Essentially, you describe what the method should do given certain inputs. Right? If it throws some exceptions, you also explain what kinds of exceptions they throw. Right? As soon as inheritance comes into play, your subclasses have to obey or have to follow everything that's written in the superclass documentation. Right? So everything that's specified in the superclass, the subclasses must also follow. Right? The problem with this is that there's nothing in the language that forces you to do this. Right? And so this requires that the programmer pays careful attention when they decide to override methods from a superclass. Right? If the programmer does this correctly, right, then that allows the programmer to write code according to the contracts of the superclass, right? And that code works for whatever subclass gets made up, regardless of who makes up the subclass, as long as they ensure Liskov substitutability still holds. Right? So, in inheritance, you have to consider what are the class invariants of the superclass, right? What are the preconditions on the superclass methods? What are the postconditions on the superclass methods? Right? So if a superclass has class invariants, then the subclasses get those invariants as well. Right? So the invariants of the superclass apply to all descendant classes. Right? Invariants are public features of a class, right? They are inherited. If your subclass fails to support the invariants of the ancestor classes, right, then anybody who wrote code according to the ancestor class documentation, their code now potentially breaks. Right? That person is not in the position to fix the code because the failure is in the person who wrote the subclass, not who wrote the ancestor class. Right? So the problem in this case is someone has overridden a superclass incorrectly. Right? Okay, so the counter class, it has an invariant. Right? It says the value of the counter is never negative. Right? So looking at the counter class documentation, you can write the following method. Right? I'm going to write a method is_odd. It determines whether or not the counter C, its value is odd. Right? This should work for any counter object that's passed in, regardless of the actual type of counter. Right, so how am I going to do this? Well, I'm going to take the value of the counter, I'm going to divide it by 2, and I'm going to look at the remainder. Right? If the remainder is 1, it's odd. Right? This will pass every test you throw at it. Right? You can make a counter having every possible value. This method will pass. Right? So this method is technically correct. All right, now someone decides, hey, look, I've got this counter class. I'd like the counter to count down instead, right? And instead of counting from maximum value down to 0, we're going to count from 0 down to min value, which is negative. Right? When it hits min value, we're going to wrap around to max value. That violates the class invariant of counter. Right? But it's super easy to do. Right? Here's my descending counter. Right? Call the superclass constructor, call the superclass constructor. Advance just subtracts 1 from the value. Right? As soon as it hits minimum value, it wraps around to maximum value. Right? This will compile. The compiler will happily accept this. Right? Now, what happens when you make a descending counter? Right? So I make a new descending counter, its value is 0. I call advance, its value is now -1. Right? I take that counter and I pass it to is_odd. Right? -1, divided by 2, take its remainder is -1. It's not 1. So is_odd now returns false for that counter. Right? Even though the value is odd. Right? -1 is odd. So this should return true. Right? So the method that was, or is, technically correct, at least according to the contracts of the counter class, now fails when you pass it a descending counter object. Right? Code that was, or is, technically correct, now produces the wrong result. Right? It's not, strictly speaking, the fault of whoever wrote is_odd. Right? It's whoever wrote this code here. Right? You can write this code. The compiler won't help you. Right? It's the programmer's responsibility to check whether or not that line of code there satisfies the class invariance for that class, right? As well as that class. Right? It doesn't, so any code written using counter potentially fails. Right? Now, you can make the argument that this is a bad way to implement is_odd. Right? So a better way to implement this would be to do C value remainder 2 not equal to 0, right? And that now works for the descending counter class, right? But this is technically correct because the value of a counter can never be negative or is never supposed to be negative. What time do we have here? Okay. Right, so that's class invariance, right? If your superclass has an invariant, your subclasses get them too. Now, that doesn't mean that the subclasses have to have the exact same invariance, right? The subclasses are allowed to change the invariance, right? As long as the modified invariants still satisfy the ones that they inherited, right? So for example, you can make a range counter that instead of counting between 0 and integer max value, right, counts between some range of non-negative values, so say between 5 and 10. Right? That still satisfies the invariant of the superclass. Right? The invariant for counter says the value must be positive. Right? Well, a range counter is always between 5 and 10, so that invariant is satisfied. Right? Range counter adds its own invariant. Right? The value of the counter is always between some minimum and maximum value. That's fine. Right? As long as the subclass still respects the superclass invariant. Oh, sorry. Right, this is easy to do. You can cook this up with very little effort. Right, add a couple of fields called min and max, and create a constructor that sets min and max to some appropriate value. Right, advance checks whether you're between min and max. Right. I think I'm going to stop there because this is going to get into preconditions and postconditions. So rather than stopping halfway through something, I'll just call it quits there, and we'll pick this up in the next lecture. All right, any questions on today's lecture? All right, I guess I'll see you on Wednesday.